So let's start. Good morning. Welcome, everybody. And thank you for being here, first of all. And first of all, let me thank Massimo Gurioli, who organized with me this workshop, and the Italian Physical Society and the Italian Society of Optics and Photonics, who supported us in the organization of this workshop in the context of the International Day of Light, which is today, the 16th of May. Let me say a few words on the idea of this workshop. The idea came up with the finding, or let's say the discovery of a Lippmann, an original Lippmann photograph in the archives of our Department of Physics. And basically, Lippmann photography is a way of reproducing colors in a photograph using interference. In a similar way, you see colors on the surface of a soap bubble. To say it briefly, but later Massimo will explain this better. And studying the work of Lippmann, we realized that his idea, which is almost completely unknown today, but won the Nobel Prize in 1908, was not only a beautiful idea by itself, but it was also an important step in the study of interference, and led decades later in the 50s, 60s to the development of holograms by Gabor and others. So we thought that it worth it to share with you, with our community, this knowledge of the Lippmann works, and also the photograph that will be in the exposition of the department. And why virtual reality together? Because we also thought that photography in general, but also, but in particular, Lippmann photography, holography, are steps in the, let's say, the desire of human beings of reproducing and representing reality in some way. A journey that started 30,000 years ago with the cave paintings that are incredible. They are not only static paintings of animals, but they are drawn in such a way that you see them move when they are enlightened with fire. So they are already a sort of virtual reality, so an ancient type of virtual reality. And so this is the link between Lippmann photograph, holography, and virtual reality. The desire of representing reality of human beings. So we can start. I think I invite here the research director of the University of Florence, Professoressa Deborah Berti. Please.
So good morning, a very short introduction because I know that I've seen the program, it's quite dense. So thanks a lot, Tommaso Matteuzzi, a young postdoc I learned, and thanks Massimo and Elisa for putting all this together. So before starting, I was upstairs with Antigone as well, and we went through the exhibition, which is really, wow, exciting. I'm really proud that you were able to put together all of these. And also I was kind of touched or excited to see the Lippmann photograph. So you are right, Tommaso. So I'm here to give you a welcome representing the rector, Professor Alessandra Petrucci, who could not make this morning. There is a Senate right now, but she will be here in the afternoon for the exhibition, for the opening of the exhibition. So it's really true that Lippmann's work is unknown. And Massimo, you told me, even for physicists, so I'm a physical chemist, and I was unaware, I have to say. And it's beautiful that he was able to, let's say, imagine this, what is call now structural colors. You mentioned the soap bubble, but I'm thinking also the peacock wings or some morpho butterfly wings. It's such a fascinating, let's say, approach also to build new materials. Being a chemist, this is my angle, so to speak. So to build new materials, like I've seen some beautiful work done with stretchable polymers and they change colors upon stretching. So it's a way you change the emulsion kind. And then I mean you get new material. So I'm thinking that it's very modern, this work. Not only it's worth celebrating because the idea was genius, pure genius, but it's really something that you can leverage to build new materials with this elegant approach. Having said that, I'm really happy that you are here in the physics department. You are so, let's say, proud of your history, and you tried even in this modern building to, preserve memories of the past. But also, I mean, this exhibition is very modern with an eye to the future. So, having said that, I think I will stay just for the opening lectures because. It's really interesting what you are doing here. So many congratulations. And yeah, that's it. Thank you so much for having organized this.
Thank you, Professor Saberti, and for welcome of the Italian Physical Society. We have Antigone Marino.
Hi, everybody. Well, so my name is Antigone. I'm in the board of directors of the Italian Physical Society, and I'm here to bring the saluti from the Italian Physical Society President Angela Bracco. Greetings, thank you. That was unable to come here. So I was lucky because I was the selected one to be here. So a couple of comments. The Italian Physical Society is promoting this initiative since 2 years, and this is the second year that Florence win. It's a competition. We received many requests. And 1 year ago, I think Nicoletta was managing the initiative. This year we have Tommaso. It's an initiative for young people because we want members to be somehow active and active in their own habitat, okay? So they can promote activities at a local level. The Italian Physical Society is a pretty small one. We have just 1,800 members, so it's a small one, but a big one respect to how many physicists there are in Italy. And I think, I joined the board of directors since 5 years, and I realized that the strength of CIF are mainly the research that we do in Italy since long time ago. CIP has 125 years. The second one is that we are a publishing company, and I think that today we will speak a little bit of this. And the third, that we have many sister and brother societies, like the Italian Optics and Photonics Society that is promoting this initiative with us. Now, I want to share 2 comments about this, the Lippmann photo. The first one is that Massimo and the team from Florence contacted the CIF to check if there are some documents in our archives, okay, like gray literature, letters that Occhialini and Lippmann probably shared together. So we hope we can really help your research to find if there is anything interesting. The second comment is that I have a passion for photography since I was a teenager, okay? And when I saw the picture upstairs, I thought, oh my God, this is a color image done in 1910. It's unbelievable. And sometimes I ask myself, will really holography be the future? I mean, new generation probably will receive a WhatsApp hologram. Is it really possible, or it's just fiction? For the moment, it's fiction. But then, if I think that a picture like that one with that definition was done in 1910, I answer myself. Probably we really don't know what we will see, but in communication nowadays, every message needs an image. Now we live in a visual society in which not just the advertisement, also now we see that a journal, a publication has more impact if you have beautiful images inside. So photography and communication by images is becoming a really important part of our society. And this is a thought I have, and I hope to see an hologram sent by WhatsApp in the future. Yeah, so thank you.
Thank you, Antigone. And we can go on. I think we can start with the scientific part. So for the first talk will be in remote. It's from Anina Anouk. Anina is an historian of art. In particular, she's an historian of photography. She is a curator of analog and digital media at the Well Museum in Vienna. And her current research interests focus on history of photography and cinema. Anina is an expert of history of Lippmann photography and is the editor of the book Gabriel Lippmann's Color Photography. I don't know if we have a copy in the end or not. You have a copy of the book, okay? So if you are interested. And so Anina Anouk, Lippmann's photography and historical overview. Please, Anina.
Hello, everyone. I hope you can hear me. Is the voice okay? Yes? Okay, perfect. So hello, everybody, and thank you very much for waking up so early to hear me talk about Gabriel Lippmann's color photography. I would like to start by thanking Massimo Gurioli for inviting me, Giovanna Pacini for the organization, and Tommaso Matteuzzi as well. So it's a real pleasure for me to be here today. I am in Vienna, but since I lived in Lucca, right next to Florence, I really hope to be able to go back and see you one day. And this talk will last around 25 minutes, after which I look forward to your questions. Potete chiedermi in italiano e cerco a rispondere anche in italiano, ho un mix tra l'italiano e l'inglese perché ho dimenticato qualche parole, perché stavo nella Germania e adesso nell'Austria. Okay. So, to give you an impression of what my work looks like right now, I am writing a book on the history of color photography in Imperial Germany, focusing on the relationships between the Lippmann process and three-color photography, from the perspectives of the history of science and the history of art. So as you can see in this meme here, which I made because I am a millennial, the biggest knife or the biggest threat coming towards the historian of color photography is the Lippmann process, because it is historically less researched. So it's a bit challenging to know where to begin working on it. And so because in the year 2021, it was the centenary of Gabriel Lippmann's death, I took part in two initiatives to promote his work and to bring my research to fruition. One was working on my book, Gabriel Lippmann's Color Photography, Science Media Museums, which was published in 2022 with Amsterdam University Press, as well as an exhibition I curated at Preuss Museum, National Museum of Photography of Norway, in which I presented, along with my colleague Jens Gold, Lippmann plates made by German practitioners Richard Neuhaus and Hans Lehmann. So this renewed interest in Lippmann really took off in 2021, thanks to the centenary of his death. And so my talk expands on the research I have done back then, and I will present the context, the historical context of Lippmann's work, and very briefly his international reception at first. And then I will present to you the optical media which were used in order to visualize Lippmann plates. And what does this mean for its reception? Traditionally, the story of Lippmann photography begins on February 2nd, 1891, at the Academy of Sciences in Paris. And it is when Gabriel Lippmann, who was a professor of physics at La Sorbonne and mathematical physics, presented a color photograph of the light spectrum. So Lippmann used this color image to prove that he has succeeded in recording standing waves using silver halides and albumin as his photographic emulsion, and shortly followed by him using collodion and gelatin as a photographic emulsion. And just to remind you, a photographic emulsion is basically a photographic binder and a light-sensitive agent. But which photographic binder with which light-sensitive agent was the million-dollar question that plagued photographers. So Lippmann's intention was not only to develop color photography, which until that time had been very difficult, almost impossible to achieve. But his purpose was also to expand upon his studies of acoustic waves, which date back to around 1880s, into the realm of light. So he went from acoustic waves to standing waves. So how did this happen specifically? Also, for the record, like a lot of physicists throughout the 19th century, he worked a lot on electricity before. So how did this happen? Lippmann knew that in order to record light waves interferentially, he would have to freeze light, to use the words of astrophysicist William Altshuler. And he could do so by creating standing waves whose maxima and minima could be recorded in a photographic emulsion. But this brought with it numerous practical problems. Why? Well, because standing waves are tiny. So the emulsion Lippmann would have to use would have to have a good enough resolution to resolve the maxima and minima separated by a half wavelength of color to be recorded. Since the visible light had wavelengths of between 400 nanometers for blue and 700 nanometers for red, the resolution of the emulsion would have to be three things. First, it has to be panchromatic, which means capable of capturing all visible light, or light visible to humans, to be specific. Second, the emulsion needs to be isochromatic, in the sense that it is as sensitive to red as it is to green. Otherwise, one part of the photo will be saturated and the other part will be too light. Third, the emulsion needs to have a resolution higher than 5,000 lines per millimeter in order to be able to record the shortest waves. So here we're talking 5,000 lines per millimeter, and for comparison, a conventional film has something between 100 to 300 lines per millimeter. And thanks to this very high resolution, the emulsion used to make Lippmann plates can and is used today to make holograms. Some would argue, and this we can debate, that a Lippmann photograph is itself a hologram that instead of recording depth, it records color. And I think in this slide, you can really see just how high resolution, the high resolution that the emulsion can reach. And I had the very big pleasure of curating this plate, and it shines from the inside. You almost don't need any light in the room. It's just really brilliant. But the emulsion is only a tiny part of the photographic process. Luckily, you can make a Lippmann plate using a traditional camera like the one you need for wet plate collodion. But you need to put the sensitized glass plate inside a special plate holder filled with mercury. And here, mercury, it's liquid mercury, not mercury fumes used to develop the daguerreotypes. And so usually this is done with a reservoir bottle that is connected to the plate holder by a rubber hose that you lift up, as you can see in the illustration here, a bit like an intravenous injection at the hospital. The plate holder has a small window through which you can see just how much mercury you got in there. Inside of this plate holder, you should be able to pour mercury in such a way so as to form what Lippmann calls a mercury mirror. And this mercury has to be in perfect contact with the emulsion. So if in a museum collection or university collection, you find a plate holder for Lippmann photography, please use hand gloves because most likely mercury was in it and you don't want to risk it. So the emulsion side and the mercury side have to face each other. The emulsion does not face the lens the way it is usually done in other photographic processes. But because the emulsion is so fine-grained, as I mentioned, the exposure time can be very long. And it ranges from anything between 2 minutes to a mind-blowing 3 hours and 15 minutes, which is the longest exposure time record that I have found in my research. In case you're wondering, it is in fact longer than Andrei Tarkovsky's first film. So you better have a tripod with you. And after you take the photo, you can develop the plate, and what you end up with is a direct positive on glass, so no negative, that cannot be reproduced on paper, and that is difficult to look at unless you are looking at it or beholding it from a specific angle because of the surface reflection, which is the unwanted light reflected from the top surface of the emulsion, which interferes with viewing the image. The inability to reproduce Lippmann plates on paper was, of course, a contributing factor to its commercial failure. But it was not the only issue. The fact that Lippmann, for some unknown reason, would not patent the process is another issue. So this meant that there was less commercial incentive for industrialists like the Lumière brothers, with whom he worked between 1892 and 1895 to continue developing it. So Lippmann's argument was he wanted the process to be available to everyone, and so he published about it and he would not patent it. Arguably, he could have filed for a patent and then transferred the right to the Sorbonne University, and then it would have been public, but he didn't do that. This is interesting, and it cannot be explained. My book puts it out there, but we don't really know why that is. But keep in mind that Wilhelm Conrad Röntgen would also not patent X-ray photography. So there is a really interesting research topic to be done there as to why some physicists would not patent their work. Moreover, one aspect that is crucial here and that often gets ignored is the fact that Lippmann was a Jewish scientist. He was born in Luxembourg, as some of you might have read on Google. The Lippmann family really struggled with being able to vote in Luxembourg, and their efforts to settle in this country were thwarted. Gabriel's father, Isai Lippmann, was excluded from the electoral roll to vote in his community in Hollerich in 1845, the year Lippmann was born, because he was Jewish. Fed up with anti-Semitism, the Lippmanns moved to France. And they were actually quite rich. They had their own manufacturing plant for leather. So they weren't this working class family who moved from Luxembourg to Paris at all. But France at the time of Lippmann's life and work on color photography was no Jewish person's safe haven. In fact, Lippmann's research about color photography unfolded in the shadow of the Dreyfus affair, which polarized French society. Through anti-Semitism and a spectacular miscarriage of justice, Captain Alfred Dreyfus was sentenced to life imprisonment for treason, having allegedly divulged French military secrets to the German Empire, something which we know today was not true. Lippmann was a Dreyfusard who asserted publicly Dreyfus's innocence, and he paid the price for having done so. At the time, the continuous rise of the French far right, with its xenophobic, chauvinistic, and anti-Semitic overtones directed at former Dreyfusards, made Lippmann the target of La France Profonde. La France Profonde is a proto-fascist set of ideas underscoring the importance of rural life away from the centrality of Paris. And it's a reactionary movement that royalist journalist Léon Daudet really championed. Due, among other things, to Lippmann's support of his former student, Marie Skolodowska-Curie's desire to be nominated as a member of the French Academy of Sciences, Lippmann was repeatedly attacked in the conservative press, and Léon Daudet called him, and I quote, the Jew of color photography, end quote. And this was published in the right-wing journal L'Action Française, organe du nationalisme intégral. The variety of insults hurled at Lippmann amalgamated his position as a professor at La Sorbonne, his Jewish identity, his contribution to color photography, and his more liberal political views. Yet, when Lippmann finally won the Nobel Prize for Physics in 1908 for interferential color photography, the French press considered his success to be a national and a nationalist victory because he won against the candidate of Germany, quantum physicist Max Planck. Thus, Lippmann was in this really ambiguous situation of being the poster boy for the supremacy of French physics within the Franco-German rivalry. But in France itself, he was belittled and shamed on a variety of levels for being Jewish. To go back to 1891, so the year Lippmann puts forth his color photograph. Not 2 months later, across the Rhine in the German Empire, German photochemistry professor Hermann Wilhelm Vogel presented Lippmann's work to his colleagues at the Physikalische Gesellschaft zu Berlin, the Berlin Physical Society. And thus began the reception of Lippmann in the German Empire and in a variety of other countries. Therefore, Lippmann was not an isolated scientist stuck in his laboratory in Paris whom nobody knew about. And I think this is how we can integrate the relationship that he had, or the exchange, at least between him and Occhialini, already right after he presented his research results in 1891. People quickly knew, thanks to the scientific press, about his work, and he started communicating with a lot of other scholars internationally. Through the scientific press at the time, researchers far and wide became familiar with his work, and they reproduced his research results by repeating the steps needed to create a color photograph, which I mentioned to you, and which Lippmann published. Most practitioners of Lippmann photography kept the process more or less the same as what Lippmann suggested. But one aspect which they did change was the use of mercury. For example, Hermann Krone in Germany, Edmond Rotet in France, Herbert Ives in the USA used air instead of liquid mercury as a contact surface with the emulsion. And this is also what Philippe Alves uses today, whom I had the great pleasure of interviewing for my book and of curating this plate for the exhibition in Norway as well. So, of course, using air instead of liquid mercury is, well, less dangerous and more practical. But not using mercury gives you an image that is a little bit more matte and less luminous. So it's a bit of a trade-off. And what is interesting is that Lippmann photography was difficult to practice for people who were not very rich. In the photographic press at the time, there were warnings that if you are using Lippmann photography and you sleep in your studio, it's not a good idea, because if you drop mercury on the ground and the sun hits it, you start to have mercury fumes, and you're asleep, you can end up with neurological problems. So there were these warnings in the press. As I mentioned, the Lippmann plate is a direct positive on glass. It is fragile, it is unique, it cannot be copied, and it cannot be printed on paper, although there is one exception to this that I can talk about in the Q&A. So other than sending the photo per post to your friends and colleagues individually and hoping for the best, what are photographers and scientists to do if he or she want to protect and present their work to others? So you have to think about always these two things. How do you protect the photograph, but how do you show it to people? So you basically have three options. First, you can glue a glass prism on the photographic plate in order to mitigate the surface reflection, and you do so using Canada balsam, as you can see in these two photos. And this is my hand in Berlin holding Lippmann plates, 3 of them that I found in the archives. Second, you can use specifically designed viewers, so a bit like with stereoscopic photographs. And in this case, in the case of the slide, these were designed by Hans Lehmann for Zeiss. He was the head of research at Zeiss, and he created Lippmann projectors and a viewing apparatus. And so you take the plate with the prism on it and you put it inside the viewer, and then hopefully you and your family or your close friends can look at it. But how practical were these viewers is a big question. Some of them are lights, and you can put them on your face and walk around. But some, like this one, weigh a mind-blowing 7 kilos. I have seen this viewer in Munich, and it is 7 kilos. Ryanair will not let you take it as luggage. Third, and this is my favorite option, you can project the Lippmann plate using an episcope projector. But before I get to projection, you should know that these 3 options are media. So they are devices designed to communicate the photo and the research results to people who do not know it very well or who are interested. In the lab or in an in vitro situation, scientists, instead of using a glass prism or before they attached the glass prism, merely put the Lippmann plate in a tray which they filled with a liquid that has roughly the same refraction index as glass, so around 1.5. And this would be benzol or xylene, to be able to look at it properly without being bothered by the surface reflection. And this they did based on the recommendations of German physicist Otto Wiener, who was also researching standing waves at the time. So the method of putting a Lippmann plate in a tray filled with benzol, it works in a lab context, but you're not going to take the tray to a party and show it to your friends. So it's not a medium from the perspective of media studies, but it is a scientific strategy. So the problem of sharing Lippmann plates with others is only solvable by projection. But projection is very tricky to investigate for historians. It is an ephemeral event that leaves little to no historical traces. For example, we do not know who was in the audience, what was the order in which the color photographs were presented, what did the photographer say when they presented it, and how did the audience react? We don't know these things. So even the most detailed review of a projection session, which took place at the time, cannot give us this type of information. And this fact is one of the reasons why projection is often neglected by photography historians who prefer to study print media. By the time Gabriel Lippmann first revealed his color photo in 1891, in the USA, William and Frederick Langenheim had already been projecting photographic slides since 1845. So projecting black and white photography was nothing new per se in 1891. People had been doing it for several decades. But for its time, the novelty in the projection of Lippmann photography was that it was a mechanical color photograph being shown and not a hand-colored one. Yet, not all projectors could project a Lippmann plate because it is in a glass prism and because it has numerous silver layers in its emulsion. And so, and I quote, "These layers reflect the light rays like a mirror in a certain direction, pulling them one way and pulling them another," end quote. For this reason, the Lippmann plate should be considered closer to an opaque object than it is to a photographic slide. And as a result, it needed an optical lantern capable of megascopic projection of opaque objects, so an episcope. If you were to use a traditional projector of photographic slides, you had to modify it and increase the amount of light it could transmit. And then you had to make sure that the light does not go through the plate, but it bounces back from it. So it becomes an epidiascope. And this is an epidiascope. It is a projector that can project opaque and transparent objects both. And here you can see that some projectors, like this one by Zeiss and the one next to it, which is by Schmidt und Hensch, had adjustable parts. So you could put an opaque object or you could put a photographic slide. Unlike today, around 1900, projectors were so expensive that they needed to be funded by camera clubs through the donation of the club's members. So an individual could not buy a projector, which is very sad because I have one myself, but not a historical one. For example, the Berlin Photographic Society, the Fotografische Vereinigung zu Berlin, purchased in 1894 from the company Schmidt und Hensch such an optical lantern. It had a strong light source, 3 condensers of 16 centimeter diameters each, an adjustable part which could accommodate the Lippmann plates' different sizes, 6x9, 3x11 for spectrographic plates, and 9x12. And of course, the Vereinigung, the Berlin Camera Club, put the projector at the Museum of Ethnology in Berlin at the time, which was a public institution and still is today. So I went and I looked through their archives, and there was this really big question about the cooling system of the projector. Because the light source, like arc lamp, would make the device overheat, there was a lot of worry about it exploding. So the museum asked the camera club to contact Siemens, which of course existed at the time, and ask for a technical review as to how much danger does the device present to the audience attending the projection sessions. And so what Siemens suggested and what ended up happening was that firefighters were present at all times during the projection session in case something went wrong so that they could evacuate the museum. So the danger of the heat and the cooling system, which wasn't perfect, was very much an issue. So projection and the Lippmann plate were a match made in heaven, and I will tell you why. The problem with projection is when you project any image, you magnify it. And in the case of hand-colored slides, for example, you can see when the hand coloring is sloppy, you can see when the colors have faded, you can see when the contouring of the image was not well done. So projection and magnification often revealed all the imperfections of a photograph, especially one with the surface painted over it. But since the Lippmann plate is not hand-painted, and since the colors are mechanical, it dazzled its audience. This is a self-portrait by Richard Neuhaus, who was one of the best practitioners of Lippmann photography in Berlin at the time. In one of the sessions which the Berlin Camera Club held, photographer Richard Neuhaus once projected an image of his parrot, this iconic one, magnifying it by 2 by 2 meters in size at the Museum of Ethnology's auditorium, which was filled with 500 attendees. So instead of the viewer, which only you and your friends and family can use, projection allowed the image to reach 500 people at the time, and it was a blockbuster event. And when you see this image magnified to such a size, it is a proof that it is not hand-colored. So there is no doubt. And this was an issue because at the time, a lot of photographers were claiming to be making color photographs, but when people would repeat their research results, it was in fact hand-painted or they messed around with the negative. So it was not mechanical color. But projection was not only used for commercial settings to entertain the bourgeoisie. Neuhaus, the following year in 1895, used projection again at the Berlin Physical Society. And during this famous session, he projected several plates, such as the spectrum, the parrot, his house, in the presence of some of the big names in physics at the time, in order to convince them of the stability of his results and the fact that he mastered the Lippmann process so much so that he produced not only one good photograph, which, you could say it's an accident, but several. So the seriality that projection enabled, as in being able to display several photos one after the other, along with the magnification of the photograph, gave credibility to Neuhaus's experiments that engendered not one, but numerous iconic photographs. And this way, to conclude, the Lippmann plate, which could not be copied or printed, still reached an audience who enjoyed looking at its beauty, was curious about its science, and eager to discuss it. Thank you.
Thank you very much, Anine. Are there questions for Anine? I think there is one from Felipe, who wrote in the chat.
Philippe is asking, why does the epidiascope have a skull? And I will tell you why. It is because it was used in two disciplines that relied on human remains for their studies, and this included biology and anthropology. Because at the time, Germany, which was an empire with colonies, anthropologists such as Richard Neuhaus, who was primarily an anthropologist and doctor of medicine, were collecting skulls. And they were studying it, and they were studying the dimensions and the relationship between the dimension of the skull and race. And in order to augment the size of the skull, they would put it in an epidiascope. So the human remains or the skull, like the Lippmann plate, were both considered opaque objects in terms of the technicality of the projection.
Okay. Thank you, Anine. I think if you have some other question to Anine, you can do later because we are a little bit late. So let's go to the next talk. Next talk is on the history of the Florentine, of our Lippmann photograph. So we have Barbara Cattaneo and Anna Giatti. Barbara is an historian of contemporary art and photograph conservator at Opificio delle Pietre Dure in Florence and CNR Institute of Applied Physics, while Anna is curator and restorer at Fondazione Scienza e Tecnica, and together they curated the conservation of the Lippmann photo of the Department of Physics. So Barbara Cattaneo and Anna Giatti, the Florentine Lippmann plate, history and conservation. Piccolissimo. Non vedo mia nulla.
È lì la cosa.
Questo si può togliere?
Sì. Aspetta, non lo so di chi è. Un attimo dobbiamo mettere. No, ma, qual è la cartella, scusi? Eccola qua. Perfetto. Questa,
Sì?
questa è la presentazione.
Sì, esatto.
La copio un attimo sul desktop,
Certo.
se non le dispiace. Sì. Grazie. Così almeno siamo sicuri che va bene, sistemo un attimo le cose. Un attimo solo, devo sistemare la sala.
So se vorreste il piede.
Prima starei seduti. Meglio stare seduti, dagli anche questa sedia. Sì. Grazie, perché c'è un problema di microfono. Quindi.
So, good morning, everyone. Today we will speak. This is questo? This one. Okay. Good morning, everyone. Today we will speak about the Florentine Lippmann plate, his history and his conservation. The Fondazione Scienza e Tecnica is an institution born in 1987 here in Florence, with the aim of spreading the scientific culture, starting from the conservation and the study of the scientific and technological collections acquired from the Florentine Istituto Tecnico in the 19th century. Those collections have nowadays a relevant historical value. Here in the picture, we can see the main hall of the physics cabinet of the Istituto Tecnico in 1899. In the 90s of the past century, interest in historical and scientific heritage was flourishing in Italy, and the Fondazione was involved in many projects concerning the scientific cultural heritage. One of these was about the scientific instruments in the physics department of the University of Florence, particularly those that were no more useful for the research. So, in the 1991, most of those instruments, models, machines, and various objects were moved from the rooms and the cellar of the university to the Fondazione Scienza e Tecnica. What you mentioned are an induction coil made by Rumkov, another a spectrograph made by Hilger, and an electric balance. Among the acquired instruments, there was a very special object that at first glance, for sure, didn't look particularly appealing. It was the interferential chromophotography that you can see exhibited here today, and which has returned to the physics department of the University of Florence. Luckily, a leading expert of history of physics and technology of physics, as of the broad family of scientific instruments, was strongly engaged with Fondazione Scienza e Tecnica from the very beginning. He was Paolo Brenni. Paolo was able to immediately recognize the rare photography, despite its poor aspect, and saving it from the discarded object. The picture, if you look at it in a properly position, reveals a beautiful image. No inventory number was reported, but beneath the plate, we found its historical label that you can see here in the slide. The label has the stamp of the Istituto di Fisica d'Arcetri, Laboratorio di Ottica, the optical laboratory. From this inscription, it has begun a research about the provenance of the photography. Very important for this research has been a correspondence between Gabriel Lippmann himself and Augusto Occhialini, that is part of the Occhialini archive preserved here in the Department of Physics here in Florence. Thanks to the two letters, we know that in February 1914, Lippmann sent 3 interferential photographs to Occhialini for showing them to the Italian Physics Society, and that the agreement is to return the plates to Lippmann. But we also know that the return is postponed. In fact, Occhialini have to wait the next meeting of the society in March. We don't have any other information till now, but we can guess that something went different from the program. Beyond the evidence that at least this plate remained in Florence, we have another letter to Augusto Occhialini. The sender this time is Beppo Occhialini, the son of Augusto. It is impossible to understand the meaning of everything written in the letter. But we can deduce that the plates were still in Florence at the time he wrote. The letter doesn't have the date, unfortunately. But thanks to few clues, we can guess it had been written between 1933 and 1949. Coming back to the Lippmann-Occhialini correspondence, we highlight some peculiar aspects of the letter. The handwriting seems to be the same for both. The handwriting isn't that of Lippmann, nor that of Occhialini. Other clues suggest that the Lippmann letter is a copy. Another interesting aspect to be better investigate is the exhibition of the interferential plates in a meeting of the Italian Physics Society. Was it an idea of Occhialini, or was there an expectation in the society? To which kind of meeting refer he? For sure, not the annual Congress. For many years, the Lippmann photography was part of the Physics Cabinet permanent exposition in the Fondazione Scienza e Tecnica Museum. But interferential photography is not widely known. And as it happens for many scientific instruments, its potential has remained untapped. Gabriel Lippmann died in February 13, 1921, in the Atlantic Ocean, due to a shipwreck. Approaching the centenary of his death, in 2019, Fondazione Scienze e Tecnica came into contact with the Photo-Élysée, the cantonal museum for photography in Lausanne, and the owner of the largest collection plates made by Lippmann himself. Photo-Élysée has launched the catalogue raisonné of the color photographic plates made with the interferential process invented by Gabriel Lippmann. We soon discovered that other important initiatives were undertaken in Europe. First of all, the Anina Nusch research and publications. Then, exposition in the Preuss Museum and the Photo-Élysée Museum, seminaries and lessons during these months surely contribute to spreading the exquisite beauty of interferential photography, as well as today's workshop. But how rare are these photographs? The Florentine plate is the only one known in Italy discovered till now. But before delving into our plate, let me mention other two interferential photographs. One is preserved in Coimbra, Spain, in the University Science Museum, together with a maybe even rarer object, the iconoscope used to better observe the interferential plates and devices for taking interferential photographs. The other one is the Lippmann photograph that is part of the Sorbonne University collection. These has the same subject of the Florentine and have played an important role in order to confirm the attribution of our plate to Lippmann himself. And now I give the floor to Barbara.
Grazie, Anna. So here you can see the two plates, the Sorbonne one and the Florentine one. And the first thing that we can actually detect is that the Florentine one has conservation issues. But before talking about the conservation issues of the Florentine plate, I would like to tell you something about how the plate is made. So actually, we have a silver emulsion on a glass plate. So it is basically a silver negative. And the important part, it is the silver grains are at a nanometer scale. So it is an almost grainless emulsion, and this guarantees this very, very high resolution. The binder of the silver can be either albumen, like Lippmann did in his first attempt during the 1890s. But then he turned on to gelatin, and also collodion is reported in literature, but for sure the one that we have is gelatin based. Then the interferential photographs can have actually the glass prism, or they can be without prism. If the prism, the wedge prism is present, then it is cemented with Canada balsam on the emulsion side. On the back, in order to appreciate the image, a black varnish is needed, and generally it is bitumen, but also carbon black with a cellulose nitrate lacquer like Zapon can be used, or carbon black mixed with shellac. And then a paper tape is actually useful to seal the plate, to seal the sides of the plates. And often a white paper can be found on the back of the plate where inscriptions are present. And actually the Sorbonne plates have inscriptions that help us in understanding where actually the picture was taken, and it was the Lake of Annecy. I just come back quickly. And this is Lippmann's wife family house close to the Lake of Annecy. And there are many other plates that were taken on that side. So which are the deterioration phenomena that we can detect on the interferential plates? We can have damages on the silver emulsion. The silver can actually oxidize and redox. There can be sulfiding problems that leads to silver mirroring and yellowing of the binder. The glass, which is soda lime glass, which was the main one available at the Lippmann time, is inclined to corrosion, so there can be crizzling and weeping. Then the Canada balsam can oxidize, the varnish can oxidize, and acidity and oxidation are the main issues also in deterioration of paper. And these can have effects also on the physical aspects of the plate. So the physical deterioration actually is mainly due to mechanical damage that can have occurred over time, basically poor handling of the plates or by accident. And so we can have again, we can detect again scratchings on the emulsion, or scratches on the glass, for example, cracks and losses, or sometimes also the using of the Canada balsam while the plate was actually, while the prism was cemented on the plate, can eventually determine some problem and issues. And then again, any kind of, for example, saliva or any kind of inclusion that can be between the emulsion and the prism can provoke over time stains and the growth of microorganisms. Insects are not really the issue in this case. So this is actually the plate, the Florentine plate. Here you can see it in reflected light, so it is basically a black, almost transparent glass. In transmitted light, we can appreciate the losses of the varnish. But what's actually struck us, it was that when the image is viewed correctly, we can detect some orange stains that are not visible, I mean, are not easy to relate to the losses of varnish. So we started thinking about the conservation treatment in 2020 when the catalog raisonné from the Élysée Museum started to be programmed. At first, we thought about doing the conservation treatment at the Opificio delle Pietre Dure. But then the plate was returned to the University of Florence, so it was just easy and attempt to do an in situ treatment here. But first, we did some analysis to the Institute of Applied Physics, Nello Carrara, which is the National Research Council, and it is just basically around the corner. So it was really handy to do that. And we had some results in using FTIR in reflectance modes as far as the bitumen is concerned, because actually it could be confirmed the nature of the varnish. But we had also some loose fragments of the varnish, and that was actually, and it was black actually, but it was detected as Canada balsam. So probably we thought that the Canada balsam had been used at a certain point of the plate's life, maybe during the 20th century, maybe to paste again the paper on top of the varnish, or maybe to try to reposition some fragments of the varnish on the plate. While XRF measurements didn't give much results, they confirmed though the soda-lime nature of the glass, and we can see that because of the high peaks of calcium and iron too. So then, after we brought back the plate to the university, we started the visual examination, and here you can see actually the losses of the losses on the varnish, and under microscope actually we could see that all the orange stains are due to basically air bubbles that are created underneath the varnish due to microfracture that are present in the varnish. So we started the in-situ treatment itself, and with the dry cleaning and wet cleaning. And for that, we used just the hair pump, paper points, few sponges that are makeup sponges, both on the prism side and so on the glass side, let's say, and on the varnish. While a solution of water ethanol, it was used to clean the surface of the prism, and it was locally used in a certain area of the losses where the glass was visible. And then we started to do the consolidation. So what we saw, it was actually that the fragments were quite loose, so we needed to block them in position. So we decided to use Aquazol 200 in a 5% solution. And it is really interesting, Aquazol. It has been widely used, especially for painting restoration. It has thermoplastic, it has thermoplastic properties, and also it has the same index, refractive index of glass. So we successfully consolidated the edges of the losses. We first tested the consolidation that we're going to perform later in the next months, because we noticed that if we percolated some consolidants within the fracture, within the microfracture, we could actually reduce the orange stains, which means that we could actually get rid of the air and have again the adhesion between the glass and the varnish. But we still actually need to do some mock-ups, and we need to try a different percentage of consolidants, because if the 5% in Aquazol 200, which has a low molecular weight, could help in the penetration of the consolidants, but it was not enough to make just one treatment. So we need to redo the treatment, so we need to adapt the method. And then we need to do also some new research on cracks and microcracks of the black varnish, and also to try to predict a deterioration pattern, because we know that it's going to crack evenly in a while. We don't know when, but it's going to happen. And then we need also to research on black acrylic paint that guarantees the right, mainly the total light absorption, in order to have a good visibility of the plates, and then make a cradle in a PETG for the permanent exhibition here. And we have already advised to use a light on demand display case with 100 from 100 to 150 lux, which is the amount of light that actually can guarantee the good visibility and the astonishing results of the colors of the plate. And that was actually advised by Jens Gold. You can see, you can read it also on the book. which I advise you actually to read because it is a very complex work, and it is an exhaustive work on Lippmann's photography. So thank you very much.
Thank you, Anna and Barbara. Are there questions? You can stay here.
There is a question from...
Okay. So, why not remove all the varnish?
No, it is
okay. It is a lot of varnish, but the parts that are only visible by reflection have the varnish detached from the glass.
I'm sorry.
Why not remove all the varnish?
It is well, so actually, the orange stains that you can see, and I'm going back in order to show you the image, Philip, that is. So the parts that you can see inside the rectangular yellow shape are actually air bubbles, while the one on the side, I don't know if I can point it some way, I don't know how to do that. But let's say that on the sides, we actually have the loss of the varnish. We cannot really remove the varnish because it's part of the object itself. So being a cultural property, it is the original varnish, and we cannot do it. So it is an ethical approach, the one that we are using. But we are confident to reduce the stains, and we already noticed that if we position a black board behind the plate, we can actually reduce the stains. And I'm really sorry we didn't put inside the presentation, and let's say after treatment, at least up to now after treatment with the blackboard. But really the visibility is much improved with a black backboard.
Okay, thank you so much.
Okay, thank you very much. So for the next talk, okay. For the next talk, I don't see Massimo because. Okay, so the next speaker is Massimo Gurioli. So Massimo needs no introduction. He's professor here at physics, and we're. Sì, sì. Eccolo, Massimo, please. Questa è la tua.
No. No. Vedo un no, lo muove sto mouse. Ecco. Ok, can you hear me?
Massimo,
sorry.
il titolo Massimo Gurioli. Dove sei?
Physics of Lippmann.
Physics of Lippmann.
Okay. So, okay, my role here is to try to explain a little bit of physics, which is quite simple, but I try to use very basic terms because we have to understand better. But since one talk about the link between Lippmann and holography is missing with respect to the original program, because if Gente cannot join us, I'll try also to add this part at the end and to make the link between these kind of photos and holography. Can I close this?
No.
No. Okay. Yeah. Okay, so what's the Lippmann idea? In terms of physics, he realized a pixelated interferometric mirror in the depth of the plate, so that each point could reflect the correct color of the real image. And to do this, use a kind of Bragg mirror, we call in physics one, and I'll try to explain you a bit about this. So the first thing, if you have interference, if you sum two waves, here I put two very simple waves, sinusoidal waves, so monochromatic waves if they are light, and I do the sum between the two while translating one to respect to the other. And you see that when a maxima corresponds to a minima, you have zero. So this is the distructive interference. And you can say light plus light is equal to dark. While instead the two maxima overlap, you have a double in amplitude, but the intensity of light is the square of the amplitude, so you have light plus light equal 4 light. So the mathematics with light is quite weird, but our physicists know this. And this is the trick to use interference to have a Bragg mirror. Indeed, if you have the soap bubble we have seen before, you have layers of a given index of refraction, and you have to sum up the reflection from the first surface and the second surface. And if happens that these two waves are in constructive interference, you will get 4 times reflectance. So if you start for 3.4%, which is the reflectance of an index of refraction of 1.45, you get 13%. While if you have destructive interference, you get 0. So interference can create color in some sense. And these are the colors that you can see in the bubble. To be correct, you have to consider multiple interference, but the result doesn't change too much if you have such a small reflectance for any surface. So you can increase the number of layers and then you increase reflectivity. So here there is a movie where you can understand that the number of layers are increasing because you see more black line on this color part on the right. And when you increase this, I put on the top the transmission in black and the reflectance in red. Of course, transmission plus reflectance is 1. And then when you have many layers, you can have a reflectance which is 1, almost 1. And it means that even if the contrast between the two index of refraction is very small, you can have a very, very nice mirror. And these are called Bragg mirror, and we use a lot of them in physics for many applications. There are optical cavities, photonic crystals, sensors, laser. So all these, let's say, devices use Bragg mirrors. And you can say that interference seems to produce colors out of nothing. So you have a piece of gray silicon. There is on the table my sample. And if you manage to put some air in the silicon and you are clever enough, you can get a bright green out of a gray silicon because you are creating an interferential mirror. So my way to say this that explain a little bit better also the final part on holography is that interference purifies light, so increase the coherence of light. And you start from white light. White light is a very poor coherence. You have a very broad spectrum. When you are able to have an interference filter or an interference mirror, you are reducing the spectrum and you increase coherence of light. And this is the trick that it was used. Another, I cannot resist to show you an opal because I'm in love with this kind of gem. So if you have a stone like this, they are done with very small sphere of glass. So each small sphere is, the material is transparent, but when you pack it together in a very ordered manner, and then you create not only interference, but you have diffraction from the single sphere, and then you have interference from all the sphere, and then you get colors. And these colors are iridescent. It means that when you change the angles, you can change the colors, and they are very bright because here reflection is extremely high. So these are the tricks under the idea of Lippmann. So let's go back to Lippmann. As Anin said, he was used to put some mercury on this setup. Here there is some video I found in YouTube that people is doing the same. So you see the mercury grows up, and then you have an emulsion on the top. So the trick is reflection from a perfect mirror. So if you have a perfect mirror and you have a light coming from, this is left, from the left to the right, which is the green one, I don't know if you see it, when you arrive to the mirror, the reflected wave has exactly the opposite amplitude. And this is done because you need to have a zero at the mirror. So the two have to have a zero at the mirror because the light cannot propagate into the metallic layer. And then these two waves, one propagating on one side, the other propagating the other side, create a stationary waves that has some zero that are fixed in space. So despite the fact that you have energy traveling on one side and energy traveling the other side, there are points in the space that you have a zero of the field. Now, the important part is that to impress a plate, an emulsion, you have to speak about the electromagnetic energy. And when you have a propagating wave, I have put in green the energy of the propagating wave. Since you have to average in time, you have a constant energy distribution along the plate. While for the stationary wave, since you have this zero, even if you average in time, you have some zero in the spatial direction. So, and when there is constructive interference, you have 4 times energy with respect to the forward wave. So you are concentrating the energy in some point, removing energy from other point, and this is the reason why when you put a plate on the first normal illumination, you have only the forward wave, so you do not have a mercury at the end. You have a grain of silver almost equally distributed along the depth of the plate. But if you have a stationary wave in the plate, then you have some position where you have more grain of silver with respect to other positions. So you have a modulation of the grain of silver, and this modulation of the grain of silver is an interferometric mirror. And then depending on the modulation you can have reflection in the green, in the red, or in the blue. Now, the beauty of the idea is that in this method with the mercury mirror, each pixel you have in the picture, so suppose you have a blue pixel, then the light coming through the plate is blue, and then the stationary wave is blue, and then the standing wave is blue, and then the mirror is blue. So you create a mirror that is exactly at the same color of the pixel you consider. So if you have a red mirror, you have a different position of the zero because the wavelength of red is larger than the wavelength of blue, and then you have position in different parts. And then if you look at the plate after development, you would find that in the blue pixel you will have that the distribution of silver grain has a periodicity, which is the periodicity of the blue, and on the red pixel you have the periodicity of the red. Now, it was very interesting studying this, that another Nobel Prize from Spain, which is Ramon y Cajal, that had the father of neuroscience, I think, he was playing with Lippmann plates, and he was doing a microphotograph of Lippmann. And this is the microphotograph you see, where there is the small square red. This is a point where the pixel is red. The small point blue is a point where the pixel is blue. And you can understand that the silver grain, which is the dark part of this image, has a different periodicity in the blue and in the red. And this is the original design of Ramon y Cajal that explain what I try to explain you. So you have more silver plane when you are in the antinodes of the standing wave, and you have 0 silver grains at the node of the standing wave. So of course, with the century of the death of Lippmann, the physicists discover again these things, and there is a very nice paper of NAS in 2021 where you can find much more detailed analysis of Lippmann, etc., etc. But I think the Ramon y Cajal was already a very good work. As for the theory, Lippmann did the theory, and essentially there is a paper, I read it, it's not so easy because the language is quite different, but essentially use the Fourier decomposition, we say physics. So any color or any light can be decomposed in frequency, and then since everything works very nicely, with this decomposition you can understand all the principle of the Lippmann. Again, in this paper, the theory is more easier to understand, to me at least, And they put also a formula that is the density of the silver grain, this part on the left part of the equation, and then it's equal to something. There is an unknown factor because in this photographic process, there are so many variables that nobody knows exactly what happens. And then there is an integral over the frequency of the power spectrum and the, let's say, standing wave, which is what the mirror creates. And the interesting part is that you don't need the metallic mirror, because if you have any mirror, you can write the reflection of the mirror with an amplitude to give you how many light is reflected, and the phase that give you the amplitude of the reflected wave at the surface of the mirror. And then here there are three examples. One is perfect metal, which is what I've shown you before. You expect to have a zero at the position of the mirror. But if you have a perfect dielectric, the zero is lambda 4 from the mirror, or you may have any other mirror. So, I mean, the separation between different grain of silver is always the same, depends only on wavelength, but the position of this in the plate depends on the kind of mirror are you using. And therefore, as Anina has shown before, there are, even in the past, there have been the idea to use just the reflection from air, from emulsion to air without any mercury. So the reflection is very small, 4%, but still the effect is there because you have this modulation that can give you the colors of from interference. However, they have shown that the rendering of the color, I don't know if this is the correct word, let's say the rendering of the color depends on the kind of mirror you put at the end. So if you have mercury or if you have air, things changes. They did the calculation, they do also the experiment. The agreement is quite good, but not perfect, also because there are many technical issues in this process. I think Philippe will tell us many of them. There are problems related to isochromaticity of the plate. You need to color sensitize dyes because silver mostly absorbs the blue and the ultraviolet, but the red is very poor absorption. So there is several problems. But I don't want to speak with this because I want to touch the problem of holography. So the second part of this workshop is about holography, and in particular digital holography. So why Lippmann is related to holography? So what is holography? When we see an object, we see the light coming from the object. So we don't see the object, we see the light. And from Maxwell's equation, from the theory of physics, the light coming from an object is completely determined if you know the amplitude and the phase of the electric field at a given plane between the object and you. If you know this, you have all the information of the light coming to your eyes. And the idea is to frozen, as Anine said, the light in a plane from the object and you, and then look at this kind of image. So Gabor take the Nobel Prize in 1951 for hologram. The laser was not invented yet, but the idea was presented. And when the laser came out, the idea is the following. You shine an object with a laser, then you have the light coming from the object in the space, and then you put a plate in between in some point, and on the plate you put the superposition of the same laser as before, and the amplitude and phase coming from the apple in this case. And then you register the interference between these two. And this is the hologram. Then if you shine again this plate with the laser, due to diffraction from this plate, the light coming from the plate to you is exactly the same pattern as the light coming from the apple. So you look an apple on the other part of the plate as the apple was there. Of course, it would be a green apple because you see the same color of the light, not a red apple, but this is the problem. And in both processes, you need coherence of light. So in the 80s, another important physicist for hologram, which is Denis Siouk, invented the so-called volume hologram or reflection hologram. And the trick is that to register the hologram is more or less the same, but then you want to use white light to see the hologram. So you have a very poor coherence light, and you want to see the hologram. So what you need is to purify the light. So you need to increase coherence. And this can be done with the Lippmann idea. So if you use a plate which is good enough, emulsion should be thick, more thick than Fiolanda, but this is not difficult. And then you should have the grain very, very small, because you need to have this periodicity lambda half very well resolved. Then if you are able to put a Bragg mirror on the back of the hologram, when you shine with the white light, the Bragg mirror transforms the white light in green light, and then you have the vision of the hologram in white light. And this is a design of what Denis Hugh do. So the object is below the plate, the light comes from the top, and on the plate you have the light from the reference from the top and the light from the object from the bottom. And so you have a counter-propagating wave in the plate, which is exactly the same idea of Lippmann. So you create a standing wave, which is very weird, very strange, because it's not periodic as before, because the wave front of the light from the object is very complicated, but still you have not only the frozen light in this direction, but you have a Bragg mirror in this other direction that purifies light. So I want to conclude with our collection of Lippmann. For the ones that are not here, they cannot visit our collection. On the left, I have a small GIF image that you can see the effect of our Lippmann in his, let's say, container that we build up for this. And on the right, I have the place from Philippe that will make a talk in a minute. And there is a table there where I put this plate. You can have a look. There is a lamp, and you can see the Lippmann plate. And I think are amazing. One of them doesn't look as beautiful as the other, which is this stripe. So Philippe take a prism, then disperse the light, and they make a Lippmann plate. You can see all the color, but it's a beautiful experiment, because if you break on this film, then you put humidity inside the film is porous, so you change the index of refraction of the Bragg, and then all the colors shift on the side. You see the difference between the two. And then if you take the time going on, what happens is that the water evaporates from the film, and the color goes back in the original position, because the index of refraction is changing with time. And I find this a very nice experiment. I will present it to my students, so be prepared. And I want to give a tribute of Philippe, because he was very, very kind to me. And this is his website. I want to thank Philippe, and I want to thank all of you for your attention.
Thank you, Massimo. Questions? Bon. No question. I think there is a question from Felipe. No. Okay.
Okay. Felipe is on the stage.
Okay.
Okay. So let's go to the next talk. We have now Felipe Alves, that Massimo has already introduced. Felipe is an architect from Lisbon, and he spent many years to explore unusual processes in photography, and in particular Lippmann photography.
Hello.
Hi. Hi.
Shall I start?
Felipe Alves, modern Lippmann plates.
Hello. Thank you very much for having me here. I'm very happy to participate. I'm an architect, and I've been working with image all my life. I worked for 20 years in computer graphics, and I did astrophotography and some holography. And to escape the world of computers, I ventured into alternative photography, analog photography, and started working with chemistry. And in holography, I found about the Lippmann process and was fascinated by this capacity of photographing color. Because I wanted to see a plate, a Lippmann plate, there was nowhere you could see it. It was very forgotten process. I decided to make my own plates to be able to see it. The first thing I tried, which is quite easy to do, was to acquire some holographic panchromatic plates. And this was my first try. It was a very emotional moment for me because as I exposed and developed, I saw the image coming up as the plate dried, and I started to see the colors like very slowly appearing. It was really, really amazing to see. After that, I was totally hooked for life by doing this process as an obsession continuously. But I decided not to go through the path of just buying holographic plates. I wanted to do my own emulsion because I find it compelling to try the process by hand with all the steps needed. I found out that you could use albumin to make Lippmann plates, so I decided to specialize myself into the albumin process. This was my first successful plate that I did. I was very happy with it. Right now it looks very bad, but I was happy I can capture some color. There's information there. And as I worked a lot with computers, if you have information, something is working, and the successes kept on gave me hope that I could improve my success. One thing that we already talked about here is this ability that this kind of photography has to photograph. It's the only process in the world that can actually photograph the shape of color. So we are photographing the intensity, but we're also photographing the frequency of the colors. And this is very compelling because the plates have so much resolution that you can photograph the shape and you get this kind of barcode. This is a computer simulation that I did. It's not scientifically accurate, but it's good to illustrate, like if you have, each color has especially mixed color, because when you use monochromatic light, you just have a continuous sine wave that is registered. But when you mix many sine waves, you get a kind of barcode of the color that you have on that zone of the plate. And this is wonderful to see, but it's even more wonderful to understand that all around us, around all objects in the world that are illuminated by light, these elements, this manifestation of light is there all around us, like the force. And it's very interesting to have this notion that we are all surrounded by Lippmann Bragg diffraction effects. Another thing that I think is important to nowadays, and it's interesting to me, is that Lippmann photography is becoming more known, and it's becoming more important in a world that is suddenly more and more photography is more dematerialized and more digital and artificial intelligence and virtual reality. It's a kind of photography that gives you a tiny world, a small object that has infinite resolution and that freezes light in it in a way that it's a very real object in opposition to all these digital dematerialized mediums that we have now. Another thing that I found very interesting in my journey of exploration, because I had to find my way through very sparse documentation. One of my main references was Richard Neuhaus's diaries, where he shows his notes and his adventure around the Lippmann process. And I could see many parallels between his difficulties, his problems, his solutions, to the ones that I found and the ones that I stumbled across. So I decided to buy a Baraband parakeet, and in honor of Richard Neuhaus, to make a similar plate as he did. It's not exactly the same, but to have this time connection between the old investigators and my own investigation was also very compelling to do. I wanted to just give a brief explanation of how I make Lippmann plates, like the basic steps needed. It's not much more complicated than is making any other traditional photograph. I could say that it could be more simple if you know exactly what you're doing. So we start with eggs, which is funny. You start with eggs and you end up with very high resolution interferential photography. And this is like, wow, it's incredible. You start with eggs, you separate the egg whites and you mix them. So you get some big meringue. After you clean some glass plates and you pour the liquid on it and you spin the albumin until it dries. This leaves us with a glass plate with a very thin layer of albumin. After that, you just have to dip it into a silver bath so it becomes light sensitive. And as Massimo told, you need, and Hani told, you need to make it panchromatic. To make it panchromatic, you use a technique which is bathing with a dye bath. There are several dyes that you use that make that sensitize the plate onto other parts of the spectrum, because mainly the unsensitized plate is only sensitive to violet and ultraviolet. So you need to push the sensitivity to other parts of the spectrum. So these dyes don't make any color. They don't colorize the plate. They just make it sensitive to other parts of the spectrum. Here are some examples of many dyes that exist. And the main thing really about Lippmann photography is that the plate must be transparent. So it's transparent because the grains are very small and very well packed together. So light goes through because it doesn't, the size of the grain is smaller than the lengths of light. And the main thing is what was already mentioned, that the emulsion must face the back of the camera and not the front. So you can have this 4% reflection instead of the 100% reflection of mercury. But 4% reflection is already enough to get a good image. And if you have the development properly calibrated, you can have very good contrast on the fringes. This is my equipment that I use. I use a very light camera with 3D printed cassettes for the exteriors. So I can just grab a small bag and go on my Lippmann trips. And for the studio, I use a large format camera and very strong lights, very fast lens. And even so, I still have to expose for 10 minutes, 1 hour between both. After exposing, you need to develop it. I use mainly the Lumiere developer, which has pyro and ammonia. It's a very fast development, it's around 20 seconds. and it forms a negative that you can see here. Usually when the plate is good, you have this brownish negative that solarizes to orange yellow on the highlights, and you have to be careful and stop it before it starts solarizing the Lippmann image also. After developing, you dry it, and then you start to see the beautiful colors coming, or nothing at all, or very faint colors, or it's very variable. When you have a successful plate, you do the necessary steps to make it even better, which is you have to paint the back with a black paint, and you have to mount it onto a prism with Canada balsam. This is really the turning point, because many plates that look good, they can suddenly look very bad when they're mounted, or the opposite. You never know. It's also a bit unpredictable. And the main thing, and the most important thing, is the display and illumination of the plate makes 90% of the plate. So if you have a very faint plate, you need a very good illumination to be able to appreciate it completely. Here is an exhibition I did in a festival here in Portugal, where you can see the rig that places the plate with the correct angle, and use LED panels for the illumination, because you only see the Lippmann image on the surface, on the reflection of the surface of a strong light. So you cannot use a point light. You need to use a luminous area to be able to see it. So I'm going to talk a bit about success and failure. This is because mainly when you start doing this kind of adventure, you only have failure, and you have the occasional success that you don't know how you did it, because there are so many variables, and we are dealing with the nanoscopic scales. So anything that is involved in making the emulsion and exposing and developing can have an effect that is it has a very drastic change in the results. So this labyrinth of variables is the biggest challenge to do this process successfully, and one way to counter it is to brute force it. So these are piles of bad plates that I've stored to remember, or to, because there's also always something good about them that I might use later. But it's nice to illustrate that to have a good plate, probably I've done 50 bad plates or not so good plates. There are plates that are faint, which they have all the information there, but it's just not strong enough. So you need very collimated light beams to be able to appreciate the colors, because they are mixed with the diffuse color of silver crystals. But actually, this image here, if you can zoom, you can read the logo on this kiosk on the beach, and you can see people lying down everywhere, and it has all the information there. It's incredible. Another thing is fogging and contamination. Lots of different contaminations and foggings and mirrorings that I find. Other thing is weak colors. Sometimes they have bright images with weak colors. I actually like the weak colors in some plates. I find them beautiful, but it's also nice to be able to control it. You can also have very strong colors or lacking colors, like this example here, where you have beautiful blues, but the greens are gone. So you have this vegetation that looks like in autumn, but it's strange, because it gives a very interesting look to the images sometimes. Also, saturation color balance. Sometimes you can have good saturation, but the color balance is off and the plate is all yellowish or greenish or bluish or reddish, because the amount of dyes that you use can determine if the plate is too sensitive to the red, it might become reddish. So it's a very delicate balance. You can see here, this is a digital adjustment to this image, and you can see that you have all the colors, but it's just the balance is off. There's also other artifacts like Newton rings or air bubbles that we can have. This is also interesting because it gives me experience about the artifacts that historical plates have. So it's a good insight for conservators to understand and deal with this kind of problems in historical plates. And also effects of poorly fixed plates. This is a very old plate that I did that was not fixed. They don't actually need to be fixed because the development action stops the plate from being light sensitive. But you can see here some silver migration forming and some fogging on this very old plate that I have that was not fixed. Some plates can really render reality with very accurate colors, but this is not always the case. There are other times that, depending on the dyes that are used and concentrations, you can see here the ground truth and two different set of dyes that give very different results. But in conclusion, because I could not spend my life doing experiments, I just had I had to combine both my work and experiment, and experiment over my work and work over my experiments in a way that I could do meaningful images and still be able to evolve on my process. And I think nowadays the errors that I get can be very beautiful and powerful and make the images more special. I can show you quickly the behind the scenes of my my plates. This is my collection of plates. I have many boxes full of Lippmann images. Some are better, some are worse. I try to give them scores, but there are many layers of scoring because you have color fidelity, you have brightness, you have the subject itself, and the quality of the albumin. So there are many many topics that you could classify a Lippmann plate. These are the unmounted ones. Most of the best I mount them. These are some still lifes that I can show. This one is actually a quite faint plate, but it's very, there's beautiful colors, and you can see here are some close-ups of it. This is a close-up of this one, and another close-up, and you could actually zoom in. I made like a small telescope to be able to go inside the plates, but it's still limited by my optics and not by the plate itself, and also by the lens that I use to make the photograph. It's another large plate. This is the plate that was created by Hanin for the Preuss Museum, which is now part of the collection. And this is the plate that is on the Musée de l'Élysée exhibition, Lippmann exhibition. This is a nice butterfly that has these iridescent colors. This kind of colors will always record better in Lippmann process. This is a close-up of the butterfly. And it's also nice to see the subject together with the mounted plate. So you have this little copy of reality. And sometimes plates look exactly like the real thing. Sometimes colors don't match exactly. Landscapes is harder. The exteriors are more elusive. The light varies a lot. There's ultraviolet that can also vary and affect the image. But I always try. I always bring some with me when I go travel somewhere, and usually 90% are bad. So it's very precious items. But even bad plates like this one, sometimes I destroy plates because I need the prisms. Nowadays, I don't have the courage to do it. Even the bad plates, I say, oh, but this has something beautiful about it, so it's difficult to destroy them. This is the difference between reality and the plate. Here's another. And portraits. Portraits is very hard to pose. On a sunny day, under the sun, you can expose for 1 minute, 2 minutes. Like this one on the picnic. This was one of the best plates in terms of color rendition. You could actually see the strawberries on the picnic. They also have, this is a close-up of these poppies here, and the camera was not that good. These are Musée de l'Élysée curators, Carol, Sandra, and Pau. And these are portraits of my wife, Ruth. Here she posed for 30 minutes each. So she's a professional Lippmann model. And this is Ruth watching some videos while posing with a glass of wine. And this is Ruth cataloging all of the Lippmann plates that I have lying around. This is another very memorable moment, which was in the Musée de l'Élysée with the LCAV team of the paper that you mentioned before, Massimo. Showing off Lippmann's plates together with my plates so we could compare them. It was incredible to have them side by side. And thank you very much.
So thank you very much, Felipe, for sharing with us your experience and your beautiful pictures. I don't know if there are questions. Okay, Antigone, please, can you come here?
Hi, Felipe. Thank you for the talk. Which is the cost, just in terms of materials of each plate?
Well, the cost of materials of each plate?
Yes, to produce one of these plates.
Well, materiality in terms of materials, the cost
behind, yeah.
It's very small. It's very small.
Like tens of euros?
Well, if you go, the glass, a glass plate, 6x6 glass plate is worth like 5 cents. The egg is 0. The silver used is I don't know, 10 cents. It's not the material price. The only thing that costs is the prism. because all the rest is just minimal. It's very small. What costs is the time that you take,
Imagine that.
the time to investigate and the time to do it, because you have to brute force it. So
Yeah, and have you ever tried to make bigger plates?
yes, I have plates up to 10 by 12 centimeters. But I like the smaller best because they have infinite resolution. So if you have a bigger plate, you just have to look it from farther away. You need a bigger light source. So angularly, you'll see the same size as a tiny plate. Because a tiny plate, you can get closer and have a smaller light source. So it's exactly the same.
Thank
And
you.
you can do more. So I tend to prefer the 6x6 format, but I can do any size up to 20 by 25.
Okay, thank you again, Felipe.
Thanks, Felipe.
Thank you.
Oh, anytime you want to visit Florence, you are welcome. So please come.
Thank you. Thank you very much.
Bye.
Bye.
So we have the coffee break now. I think